So we are in Unit 5, Balanced Forces, and in this video we are going to talk about problem solving. How do we approach problems in this unit that we're in, specifically relating to the problem solving process. So we should be really familiar with the problem solving process, all 7 steps. So drawing a picture of our situation, writing our givens, writing our unknown, picking an equation, rearranging the equation if needed, and then checking our units and solving the equation for the unknown. Specifically today, we are going to focus on steps 1 through 4. So just kind of setting up the problem. How do we set up the problem and make sure that we pick the right equation? Specifically in step 1, when we draw our pictures, remember from the last video we talked about those things called free body diagrams. The pictures in this unit for our step 1 are going to be those free body diagrams. So we're going to remind ourselves about how to draw them, what steps do we take, how do we figure out what goes into the free body diagram, but those diagrams are really going to help us as we move through the problem solving process. So we're going to do a couple examples just going through the first 4 steps, and then I'm going to do an example at the end where we go through all of the steps to actually solve for an unknown in a problem. So here we go. Our first example is Miss Nielsen is moving her 35-kilogram couch. She pushes the couch to the right at a constant velocity. What is the normal force exerted on the couch by the floor? So you might be looking at this and thinking, how the heck are we going to solve it? And really the first thing that would help us is a visual representation. So here's my picture of me pushing a couch to the right at a constant velocity. So my velocity is pointing to the right. This doesn't really count as my picture for the problem. It's just my visual representation to help you think about the problem. So we're going to walk through the first few steps of the problem solving process. So we're going to start with our drawing a picture. So drawing a picture is really important for us in these problems because the picture is our free body diagram. And the free body diagram is going to be of the couch because the couch is the thing that's being pushed on. I am pushing the couch. So my box for my free body diagram represents my couch. So we want to ask ourselves those different questions to figure out which forces are acting on the couch. So first, is the couch on Earth? Yes, it's on Earth, which means that the force of gravity must be acting on it. We know the force of gravity pulls straight down. Also, we know it's touching a surface. It's on the ground, which means there's going to be a normal force in the opposite direction. The ground is pushing straight up on the couch. And we know that the force of gravity and the normal force have to be equal and opposite. Otherwise, the couch would fall through the floor or fly up to the ceiling, which doesn't make sense. Both forces have to be equal. We also know that there is an applied force. Okay, so I am pushing the couch. That's me directly pushing the couch to the right. So there's going to be an applied force to the right. But then there must be something that is kind of resisting that force as well back to the left. So we know that the couch is moving, which means that there must be friction. We always consider friction unless otherwise stated. So the force of friction points opposite the velocity. The velocity is to the right, so the force of friction points back to the left. And again, I said that there was that applied force that pushes to the right. We know the force of friction and the applied force have to be equal and opposite, even though my arrows don't really look like they're the same length. We are saying that they are the same length because we're traveling at a constant velocity. We have balanced forces. That's the unit that we're in. So just reminding ourselves that the normal force has to be equal to the force of gravity and that the force of friction has to be equal to the applied force. So those aren't really equations. That's just based on my free body diagram. Those are statements. Those are facts that I know, which is going to help me determine how to solve this problem. So moving on to step 2, writing out my givens. I'm not really given a whole lot of information in terms of like numbers in this problem. The first number that I see is that the couch is 35 kilograms. So I'm going to write 35 kilograms here. We know kilograms is a unit of mass. So 35 kilograms is the mass of the couch, which is just M. That's kind of the only number I'm given in this problem. Another thing that we always know is when the object is on Earth, we know that it's subject to the force of gravity. And we know that the force of gravity results in an acceleration. So that acceleration is equal to 9.81 meters per second squared. Okay, so we also know that that's always going to be known to us in these problems. Our acceleration due to gravity, which is little g, is going to be equal to that 9.81 meters per second squared. And those stars next to my equations, those are also kind of knowns. We know that it's traveling at a constant velocity, so we know that those forces have to be balanced, they have to be equal. So step 3, what are we looking for? The question asks us, what is the normal force exerted on the couch by the floor? Fn. Fn is what we're looking for. How hard is the floor pushing up on the couch? Okay? So the reason why we're actually doing step 4 today is kind of because of those equations that I already wrote down. So when we pick our equation, if we're trying to find the normal force, we know that the normal force is equal to the force of gravity. We said that before, they have to be balanced, otherwise bad things would happen. So that's going to count as an equation that I'm going to use, but I don't know what the force of gravity that's acting on this couch is. But I can find it, right? We know how to find the force of gravity. We mentioned this a long time ago, but the force of gravity can be calculated with the mass and the acceleration due to gravity. So the force of gravity is equal to the mass of the object times g, the acceleration due to gravity. So what I would first want to do is find what Fg is, because if I know what Fg is, then I automatically know what my normal force would be, because they have to be equal and they have to be opposite. I know the force of gravity pulls down, so the normal force would point up. And that's how I would go about solving this problem. So our next example is Mr. Willauer is pulling a sled across the snow at a constant velocity to the right. The sled has a mass of 45 kilograms, and the normal force is measured to be 441.5 newtons. The coefficient of friction between the sled and the snow is 0.15. What is the force of friction acting on the sled? So there's a visual representation of Mr. Willauer pulling a sled to the right. So first up, our picture is going to be our free body diagram of the sled. First and foremost, the sled is on Earth, which means the force of gravity has to be acting on it. So the force of gravity is going to be pulling down. Also, we know there's going to be a normal force because the sled is on a ground, it's on a surface. So the normal force is going to point up, and the normal force and the force of gravity are going to be equal and opposite. Next up, we know that Mr. Willauer is pulling the sled to the right. In my drawing, it's a rope that he's pulling that's attached to the sled, so I'm going to call that tension. And since the object is moving, there must be something resisting it, so there's some friction there. Pulling to the left opposite the motion, we know the force of friction and the force of tension have to be equal and opposite. You could also argue that that force pulling to the right is not tension, it's applied force because Mr. Willauer is doing it, and that's fine too. Either one is acceptable, the tension or the applied force. So moving on to step 2, what are our givens in the problem? The first number that we see is that the sled has a mass of 45 kilograms. So 45 kilograms is equal to the mass m of the sled. Then it tells us that the normal force is measured to be 441.5 newtons. So 441.5 newtons N is equal to my normal force. They told me that directly. So Fn. The next thing I'm given is that the coefficient of friction between the sled and the snow is 0.15. So I'm going to write down 0.15. And we talked about this a long time ago as well. The coefficient of friction is just that number. There's no unit, but it's that mu. It's a Greek letter m. It's kind of a funky looking m thing, and we'll need that for this problem. As always, since this sled is on Earth, we know that the acceleration due to gravity on Earth is 9.81 meters per second squared. That's little g. We also know, since our object is traveling at constant velocity, and since we're in the unit of balanced forces, we know that our forces have to be balanced. So the force of gravity is equal to the normal force, and the force of tension is equal to the force of friction. And those forces are opposite in direction. So step 3, what is our unknown? What are we looking for? The question says, what is the force of friction acting on the sled? So what's the force of friction? That's our unknown, that's our question mark. Step 4 would be to pick an equation. So in this problem, if we're looking for the force of friction, there is a simple equation that we use to calculate the force of friction that we mentioned a long time ago. The force of friction is equal to that coefficient of friction multiplied by the normal force. So that would be our equation that we would use to find the force of friction. We have what the coefficient is, and we have the normal force. Also, we know that that force of friction is equal and opposite to the force of tension. So if we were asked to find the force of tension, we would want to first find the force of friction and then tension. But they're just asking for friction in this case. So that's this problem. Our last problem, I'm actually going to walk through the entire step process. So a person is pushing their refrigerator to the right at a constant velocity. The coefficient of friction between the floor and the fridge is 0.3. The fridge has a mass of 120 kilograms and the floor exerts a force of 1,177 newtons up on the fridge. What is the applied force on the fridge? So, step 1, drawing my free body diagram for my fridge. It is being pushed on. It is the object in question. My fridge is on Earth, which means that there must be a force of gravity that pulls down on it. The fridge is resting on a surface. It's resting on the ground, so there must be a normal force that is pushing up on it. And we know still that those forces are equal and opposite. Next up, we have an applied force. A person is directly pushing on this fridge to the right, and we are told that there is friction between the floor and the fridge. Friction opposes motion. Our motion is to the right, so our friction points to the left. And we know our force of friction must be equal and opposite to that applied force. So once again, I'm going to write my equalities of my forces here on the right. So my normal force must be equal and opposite to my force of gravity. And my applied force must be equal and opposite to my force of friction. We're ready to move on to step 2. Step 2, we're going to write down our givens. So the first number I'm given is that the coefficient of friction between the floor and the fridge is 0.3. So 0.3 is equal to my coefficient of friction, that mu, Greek letter M. Next up in the problem, they tell me that the fridge has a mass of 120 kilograms. So 120 kilograms is equal to M, the mass. Next up, it says that the floor exerts a force of 1,177 newtons up on the fridge. So I'm going to write down 1,177 newtons. What is that force? Well, it's the normal force. The force that the floor pushes up on the fridge is my normal force. As always, since our fridge is on Earth, we know that the acceleration due to gravity is 9.81 meters per second squared. Step 3, what is the applied force on the fridge? That is our unknown, the applied force. We are looking for FA. That is our unknown. They're asking us to find it, and we will. Step 4, now we want to find an equation that will help us solve for the applied force. So we know that the applied force has to be equal and opposite to the force of friction. So I'm going to use that equality, that equation, to help me find the applied force. But I can't directly find the applied force. I'd have to first know what is the force of friction. Because I know that those two are equal, I can actually calculate the force of friction. So I'm going to use my force of friction is equal to the coefficient times the normal force. I'm going to use that equation. Once I find the force of friction, then I can know what the force applied is. I don't need step 5 because I'm solving for the force of friction, and then I'll just use that to know what the applied force is. So moving on to step 6. The applied force is measured in newtons, and the force of friction is measured in newtons, so newtons have to be equal to newtons. And then if we take a look at our second equation there, this mu, this coefficient of friction, doesn't have any units. It's just a number. So that means our newtons are still going to be equal to our newtons. So we're good. Next up, step 7. I'm going to first find what is the force of friction. So my mu is, my coefficient of friction is 0.3, no units. I'm going to multiply that by the normal force, which is 1,177 newtons. When I plug that into my calculator, I will find that the force of friction is equal to 353 newtons. I did round a little bit there. Remember, forces are vectors, so we have to include the direction. The force of friction is pointing to the left in my free body diagram. So I'm going to write that on my answer there, that the force of friction is equal to 353 newtons left. Finally, I know that the applied force is equal and opposite to the force of friction. So that means that the applied force is also going to be 353 newtons. That's going to be its magnitude, but in my free body diagram, the applied force pushes to the right. So I'm going to put 353 newtons right. That is my applied force. It is not a complete answer unless you also give the direction, because forces are vectors. And that's this example problem.